Hi, everyone, and welcome to the first session on threshold signature schemes. We're very happy to have Rosario Gennaro here. Rosario is a professor of computer science at the City College of New York, and is currently on leave at Protocol Labs Research. He has a 25-year research career in cryptography with contributions in threshold and proactive cryptography, denial authentication and key exchange, secure election protocols, and zero-knowledge systems. For his work, he was named as a fellow by the IECR in 2020, and he was among the participants of the first Secure the Internet Awards by Facebook. Rosario, please.
Thank you, Carmit. Thank you to the organizer for inviting me. I'm very excited to teach for the winter school. I wish I could have come in person. And if I'm speaking very loud, it's because I'm excited, but also because apparently my microphone is a little weak today. So I'm compensating by speaking very loud. So today I'm going to talk about threshold signatures. We're going to start with SQL log-based schemes. This talk is more of a survey, kind of starting from the very old results, leading you to what the state-of-the-art open problems, recent works are. So bear with me if you know some of this work already. It doesn't hurt to sort of repeat them, but also I thought in terms of like graduate students who want to sort of get involved in this research area. And so I thought it would be better to sort of start from the very beginning. So let's start. So what is threshold cryptography? Threshold cryptography means cryptographic computation over shared keys. And what do I mean by that? Cryptographic computation usually are decryption and signatures. And for those computation, the knowledge of the key is the security enabler, right? To sign, you need to have the private key. To decrypt, you need to have the private key. What that means is that knowledge of the key is a single point of failure. The key becomes an incredibly attractive target to attack the system. If the key is compromised, you can forge, you can decrypt messages that you're not authorized to decrypt. So the goal of threshold cryptography is basically to take this key, break it into pieces, and distribute it among many devices, and assume that only a fraction of these devices can be compromised. And this area was introduced by Ivo Desmet in the early 90s. Around that time, there was a lot of work around multi-party computation. And for those of you who know multi-party computation, this is basically an example of multi-party computation. What makes threshold cryptography different than MPC is that we try to come up with solutions that are tailored to the cryptographic computation at hand, and so try to get something which is more efficient than general purpose MPC computation. Now, back in the 90s, that was when we thought of MPC as a beautiful theoretical result with very little practical value. This was something that was somehow made sense. And it still makes sense today, but as we will see at the end of the talk, MPC is sort of catching up with threshold cryptography. And so for certain problems, it turns out that if you just go to the regular MPC protocol and implement the cryptographic computation through the MPC protocol, we're getting to the point that the two solutions are actually, the two approaches are actually kind of competing with each other. So let me pictorially say, describe what I'm saying here. So there's a key, there's a message, and knowledge of this secret key is give you the signature. If the adversary learns the key, you can forge. And what we would like to have is put this key in many different devices, and obviously not the whole key, and I'll get to that in a minute, and the devices have to somehow coordinate to compute a signature. And during the talk, you'll see this little green references coming up. I thought that, again, given that my target audience here is students who may want to get involved into this research area, that since you guys have the slides, that will provide you with like complete references in the slides so that you can go and then read the papers to get more details. So watch for this little green references, and after the talk, if you want to learn more, you have your reference in your hand. So, the basic solution to do this is to replicate your keys. Instead of having one key, you can replicate your keys in many, so you can create many independent keys. So in this picture, for example, 5, and when you sign, each key will sign independently the message, and then what you change is the verification algorithm. You say that you accept a vector of signature if at least 3 of the 5 are valid. So if at least t plus 1 of the n signatures are valid. So this is the simplest, most general way to achieve what we're after, because now even if some servers are 2 of the 5 servers are compromised, they can only compute SIG4 and SIG5, and the verifier will never accept it because the verifier wants to see 3 signatures, not 2. So the issues with this solution is that it is somewhat inefficient. It requires replicating your cryptographic computation. So if you're looking for a T out of n, your signatures now blow up by a factor of n, and your public keys blow up by a factor of n. There's also an issue on non-transparent security policy, meaning I know what is the security policy that this server is using to sign messages. And what we really want is a system where when the message and the signature come out of the server, the verifier shouldn't know what's going on behind the curtain. It should look exactly like a single regular signature. So multi-signatures, which is something related to this concept that I'm presenting right here, address some of these issues. And if I had time, I hope towards the end of the lectures, maybe tomorrow, to address some of these issues. But I still don't know if I'm going to have enough time to also cover multi-signatures. So, so this is the basic solution. This is the reason why we're not going to use it. So what we want, as I said, is a signature that looks exactly like it was produced by a single party, but yet the keys store in share form across many devices. So, and now you should all think about secret sharing, right? So we're having this key and we're going to share it among a bunch of servers in a way that that T players have no information about the secret, and T plus 1 players can recover the secret. So, and for those of you who don't know Schnorr scheme, let me briefly recall it. Let's assume that Q is a prime. Let's assume that S is the secret, is an integer modulo Q. So what you're going to choose a random polynomial with coefficient in ZQ of the degree T, such that the free term is the secret. And then each player will receive a point on this polynomial. Now, because the polynomial is of degree T, T plus 1 players can recover the secret. They can recover the entire polynomial by polynomial interpolation. And T players have no information about the secret in a strong information theoretic sense. Why? Because for any possible secret S prime, because the polynomial is random, there is always a polynomial which agree with that particular secret and the shares held by T players, by the adversary. So this is a classic result. And so So we can share the key, right? So we take this key, we break it into pieces, and we give it to 5 servers. And now, what are the 5 servers going to do when the message comes in? How are they going to use these pieces to sign? So one idea is that, okay, we're going to put the pieces together. We give them all to one server. This server is going to sign, and then the server erase the full key, and we go back to the shared key. This is not okay. Oops, let me go back. This is okay. It's an improvement on the key being held in a single place permanently, but it's still not great because you still have a single point of failure, which is the server where the key gets reconstructed. So we don't ever want to reconstruct the key in one place because that will create, again, a single point of failure. So our goal is to compute the signature directly from these pieces that each player holds. And here we're going to use a very simple fact about polynomial interpretation, which is that polynomial interpolation is a linear function. So if you're given a set of t+1 values on the polynomial, and you want to find the polynomial that agrees with those values, then if this is a classic result of you can use the Lagrange interpolation, where the Lagrange is a polynomial of degree t defined by being 1 in point I and 0 everywhere else. And so, and this is the definition of the polynomial, of the Lagrange polynomial. Then it must be that your polynomial f is the linear combination of these Lagrangian polynomials with weights the shares, right? And because both sides are polynomials of degree t, that agree in t+1 points. So remember that we want to just find the secret, which is the free term. So take that equation and apply it just to the free term, and it turns out that the free term is a linear combination of the shares, where the coefficients are the free terms of the Lagrangian polynomials. Okay, so there are 2 things that I want you to remember from this. So, and that's the formula for the specific Lagrangian coefficients that will give you the secret by linear combination of the shares. There are 2, and another thing that this is actually true is this is true for any point. It's not just true for the free term. Any point can be written as a linear combination of the other points with the appropriate Lagrange coefficients. So 2 things that you need to remember from the slide. One, that the secret and actually any other share is a linear combination of t+1 shares. And the second thing, which will become an issue tomorrow when we're going to talk about RSA, is that this polynomial interpolation requires a field. And it requires a field because it's performing divisions. So we need to have inverse of all our numbers, of all our elements, and therefore we're going to work in a field, and that's why everything we do right now, it's modulo Q. So put this aside as something to think for later. Okay, so now we're ready to show you the first example of threshold signature, and we're going to use BLS signatures. So for those of you who don't know BLS signatures, let me remind you briefly. BLS signatures are designed over a cyclic group G of prime order Q. And the one thing that is special about this group is that we have an efficient test that is going to tell us if 2 values in the group Y and S are at the same Discrete log with respect to 2 different bases. So if you look right here, Y is G to the X, S is M to the X. In this particular groups, we have an efficient test that determine if that's true or not. And normally this test is implemented with bilinear maps, but for the purpose of this talk, we don't particularly care. All we care is that this efficient test exists, and these are called gap DDH groups, because the computational problem is hard. To compute S is hard, but to decide if S is correct is actually easy. So the BLS signature works as follows. The public key is a value y equals g to the x. The secret key is x. On input a message m, the message is hashed into the group through a collision-resistant hash function. And you actually, for the proof of security, you actually need more than that. You need to be a random oracle. And then the signature is computed as m to the x. And then the message and the signature are sent to the verifier. And what the verifier does, it uses this public test to check that m was raised to the same exponent that the public key is raised, so basically to the secret key. And the idea is that only the signer can do it. Okay, and this is the reference right here. So great. So this is how BLS works. How does threshold BLS work? So let's assume for a minute, and we'll talk about that in a second, that the dealer, that at some point the secret key sits in, somebody generates the secret key in a single place, and then it shares it among n parties using Schnorr. And let x1, x2, xn be the shares. So what does that mean? That means that there is a polynomial of degree t such that the free term is x and the point at I is xi. And everything is modulo q, which is the order of the group. So on input m, every player outputs what we call a partial signature. A partial signature is the message m raised to its share, and we call that si. Okay? Now, if we have a set of t+1 partial signatures, remember that x is a linear combination of the xi's with some appropriate Lagrangian coefficients. And the signature is m to the x. Therefore, if I plug this linear combination into here, it turns out that the signature can be computed from t+1 partial signature by this product with weights, the Lagrangians. This is called interpolation in the exponent. So interpolation in the exponent is where we turn this linear combination of the secret into a product of these public partial signatures with the appropriate Lagrangian coefficient in the exponent. So maybe this is a good point to ask if there are any questions, because this is going to happen a lot. So I want you guys to understand that we're doing what it means to do interpolation in the exponent. But up to now, it's pretty simple. So if there are any questions, let me know.
Yes, so far there are no questions in the chat.
Okay, great. So let's continue. And let's argue, why is this secure? So what is security for signature? Security for signature is the classic definition of chosen message attack. The adversary runs on input the public key, it queries messages, and it gets signature. And it does this a lot, and it queries messages and it gets signature. And then after a while, the adversary tries to output a forgery. This is a message M that was not asked before with a correct signature. And our goal is to prevent this from happening, right? So how do we know that when we move to the threshold setting, the scheme remains secure? So in the threshold setting, we have an adversary that controls a fraction of the users, in this case 2 out of 5. And the adversary on input a message M, when the adversary says, please sign M, here the adversary saw the signature S equal M to the X. Here, the adversary sees 3 partial signatures, right? And what I want to claim is that the adversary, when the adversary sees these 3 partial signatures, the adversary learns nothing more than the signature itself. Why? Because given his own T partial signature, given that he knows already M to the X4 and M to the X5, and given the signature S, the adversary has already a set S of T+1 points. And the set of S of T+1 points would allow him to interpolate in the exponent the other partial signature using the Lagrangian linear combination for the other share, not for the other secret, right? So here, the partial signature of all the good players can be reconstructed from the partial signatures of the adversary and the full signature. And this is a classic simulation argument that tells me the adversary, when he sees this 3 partial signature, doesn't see anything more than the real signature. So what I just built is a simulator that, given the correct signature, can simulate the entire view of the adversary. The view in this case is the 3 partial signatures that the honest parties contributed. So this implies that the adversary cannot forge messages in the distributed scheme unless they can forge them in the centralized one. And let me get into more detail about this argument. And everything is pretty simple with BLS, but I want you to understand this concept because they'll come up over and over again in the rest of the talk. So let's assume that there is an adversary that can forge controlling only T players. So in our case, 2. So we're going to build a simulator, and the simulator will forge the centralized scheme. So if the simulator forges the centralized scheme, it runs on input a public key, which is y = g to the x. Well, so the simulator, what is the simulator going to do? The simulator is going to take random values x4 and x5, and is going to give them to the adversary. And he said, these are your shares of the secret key. Now, remember that Shamir is information theoretically secure. So at this point, the adversary has no way of knowing that basically there are x4 and x5 that are consistent with a sharing of x. So the adversary is happy. He says, good, I got my 2 shares. And now the adversary starts the CMA game in which he says, let's sign this message M. So then the simulator takes the message M, and remember that this is a forger for a centralized scheme, is allowed to ask for messages. And he's going to go and ask for messages from his own signature oracle. And it receives back S, the little signature. Now, the adversary does that simulator that I just described in the previous slides. Given the signature, S = mx, and given the partial signatures of the adversary that the simulator knows because he gave x4 and x5 to the adversary, the simulator can interpolate in the exponent the partial signature of the honest players, like I told you before. And he outputs these guys. Up to this point, for the adversary, this game is exactly the same as if it was running a signature network with real players rather than with 3 simulated players, right? So if the adversary forges in the real life, the adversary will forge in this distributed game. But this is a message that was never asked here, and therefore this is a message that was never asked here. So this counts as a forgery also for the centralized simulator forger. So here is how you use simulation to prove that if your signature protocol is simulatable, then it's unforgeable. And if the original one is unforgeable as well. So again, hopefully there is no question up to this point, but if there are, please let me know. So we have focused on unforgeability right now, where every player outputs the partial signature M to the xi, remember? But we can interpolate only if the adversary gives me partial signatures which are correct. So the protocol that I described to you works for what we call a semi-honest adversary, meaning an adversary that follows the protocol, always does the correct thing, but is trying to learn information. And I just showed you that in this case, the adversary cannot forge. Now, if the adversary gives me incorrect partial signatures, what can we do? the unforgeability proof doesn't change. The adversary, for any t less than n, the adversary will never be able to forge, even if it corrupts everybody minus one of the servers. But if we assume a malicious adversary, how do we guarantee that the protocol always completes successfully with a valid signature without denial of service? Well, first of all, now we really need honest majority. We need that n is bigger than 2t. Why? Because t corrupted players can always even refuse to speak, right? So you need t plus 1 honest players if you want to guarantee termination, successful termination of your protocol, right? So first of all, to guarantee robustness, we need at least honest majority. But even if we have honest majorities, how do we detect which signatures are correct and which signatures are not correct? And here, let me take a small detour. I put this slide and then I realized it's really a major detour, but I decided to leave it. Turns out that, and the reason I put it here is because when I was in grad school, this problem occupied my mind for a little bit. So one interesting thing about Shamir's secret sharing is that it's an example of a Reed-Solomon code, which means that if we have enough good shares, we can interpolate the polynomial, even if there are t incorrect values. So if I give you the values y1, y2, yn, which are supposed to be fi, so if t of them can be wrong, but you have more than 3 t points in total, then you can still interpolate f of x. You can error correct those points. But we're interpolating in the exponent. And for a while, we didn't know if this error correcting feature would translate into the exponent. And unfortunately, it doesn't. And it actually later, Piker showed that this is as hard as a problem as computing the Feldman values. So there is no hope to use the error correction of Reed-Solomon codes, Shamir's secret sharing, to identify what the partial signature, the incorrect partial signatures are, and throw them out. So we need to do something else. We need to deal with incorrect signatures. Well, one thing that you can do is try all possible sets of t plus 1 partial signatures and try until you find one that yields a valid signature S. But that is an n over t solution, so it's only okay for small n and t. Well, for BLS, it's actually not that big of a problem, because if you augment the secret sharing with this commitment to the shares, if the players know yi, which is equal to g to the xi, where xi is the share held by player I, then when the player outputs a partial signature, which should be m to the xi, remember that we have a test that check if this value and this value have the same Discrete logical. We can use this efficient test also to check that. So as long as you augment the key generation with these public values, you can do that. The question is it secure to augment the key generation with these public values? And we'll get to that in a minute. When we'll talk about the security of Feldman's VSS. But if you follow the interpolation in the exponent argument, you should see that the adversary sees all these values in the exponent. The adversary has t of the shares, the adversary has the public key. All these other commitments can be simulated, are given the public key. So that's basically the argument. But we'll see that argument more carefully later. Okay. For groups where such a test doesn't exist, there is actually efficient zero knowledge proofs for this statement, and we'll get to that later again, later in the class. It will come up when we do threshold RSA. Okay. So at this point, I can't see the chat, I can't see the Slack, but I don't know if there is any question that says, hey, wait a minute.
So far, there are no questions.
Okay, but I'll put a question, because this is an obvious question. Wait a minute, what do you mean a dealer? We have assumed that there is the secret key for this BLS signature scheme, which is held by a dealer who performs the secret sharing of X. And then also this augmented public commitments for the shares. Now, isn't this a single point of failure, right? And the answer is yes. So remember, our goal was to avoid the single point of failure. But we're already improving to what I described before. So why? Because this is a one-time event. Once the dealer shares the secret key X, you can destroy all information about X once the sharing is done, and X will never be recovered in a single place ever again. So in some settings, this is actually okay. You have a very trusted execution environment. You generate the key in that single server, you share it, you destroy it, and you're done. So for certain applications, this is fine, but in theory, and actually in practice, there are applications where we want to do this without a dealer. And the answer is yes, but you have to wait. So we'll talk about it in like maybe 3 or 4 slides. And this is the topic of distributed key generation, which will come up later. Okay, so we've done BLS, let's do Schnorr. So Schnorr, again, we have a cyclic group G of prime order Q for people who don't remember how Schnorr works. On input a message M, you choose a random nonce K in ZQ and compute R equal to G to the K. Then you hash everything, the message, the public key, and the nonce, and obtain an element in ZQ. And you set S to be K plus MX mod Q. And you output R and S. This is basically a Fiat-Shamir transformation over the Schnorr identification scheme, proof of knowledge of discrete log. It's basically a proof of knowledge of little x, a zero knowledge proof of knowledge of x, made non-interactive through the Fiat-Shamir heuristic, and by plugging the message into the hash, you're also getting a signature scheme out of it. What's the verification? The verification is to take this equation for S and the exponent. And so if you raise G to the S, you should be getting R times Y to the N. Okay, so this is Schnorr. How do you do threshold Schnorr signature? So Schnorr is here. And here I had a hard time coming up with a reference. And if somebody knows, I think this was folklore, and I can't really identify the first paper that said this is how you do threshold Schnorr signatures. But probably there is one, and I can't figure out what it is. So again, let's use a dealer. We'll talk about distributed key generation in a minute. But what does the dealer do? The dealer takes X, shares it, usually a polynomial degree T, blah, blah, blah. And then when it's time to generate K, here's an interesting thing about K. K has to be secret. If K is public, whoever knows K will find X. So knowledge of K and knowledge of a signature computed with K will give you X. So K cannot be generated by a single party. It has to be generated, it has to be shared among the parties. Here, I'm going to use a dealer, which is a big problem, but just for simplicity for a minute, let's use a dealer. And now these are the shares of the nonce. And now once you have the shares of the nonce, every player can output G to the Ki. But G to the Ki, given T plus 1 of them, you can get R via interpolation in the exponent. And now the players can compute, once you have R, you can compute M and set your partial signature SI as ki plus mxi. And now, if you interpolate this si, you get the free term of a polynomial that asks for free term k plus mx, which is exactly the s that you're looking for. And again, this only works for semi-honest adversary. Okay, so here we're using the linearity of Shamir in 2 points. We're using the linearity of Shamir to compute the R as an interpolation in the exponent, and to compute S as linear combination of 2 secrets. Okay. If we want to deal with corrupteds, again, let's assume that we have public commitments to the xi and public commitment to the gki, and that will allow you to check every partial signature locally with respect to the public commitments. And at that point, you know which one are the correct signatures, and you can interpolate those. Okay? So these public values here will allow you to do basically a n of t plus 1 Schnorr verifications on the partial signatures, which would then allow you to sieve out bad partial signatures and interpolate us. Okay. That's because we're trusting these public commitments because they come from the dealer. Okay. Dealer again, this is a problem. A dealer in this scheme is a problem because the secret key is shared once, is destroyed after sharing. That's a one-time thing. But a dealer who shares the secret nonce every time is a single point of failure all the time, right? Because as I said before, knowledge of K is equivalent to knowledge of X. So this is really not okay. So we really have to do it without a dealer. And the interesting thing is that the generation of the nonce is the generation of G to the K with a sharing of K. So it's basically the same process as generating the secret key. So if we have a DKG, a distributed key generation, in principle, we can use it both to generate the secret key at the beginning and to generate the nonces during the signature generation. Okay? So let's continue. Okay, so we'll talk about that in a minute, but let me finish. Let's do this, the unforgeability proof by simulation for Schnorr, because it will tell us what property we need from this DKG. Okay, but let's do the simulation first with a centralized dealer. So we have a simulator that is going to forge the centralized key. Okay, so it gets the public key for Schnorr, is going to take 2 random values and give them to the adversary, and then given these random values, it can interpolate the exponent. By interpolation in the exponent, is going to get G to the xi equal yy for the honest players. And now we have the public commitments for everybody, and the public key is going to match y. Okay? So very important. The simulator is going to set up this fake simulated network to run on the same public key that she received from the challenger. So by doing this interpolation in the exponent with these 2 random shares given to the adversary, the network will run on public key y. Now, the adversary say, let's sign M. The simulator is going to send M to its challenger, is going to get R and S. Now, the simulator as R is going to give random Ki to the adversary. And then does another interpolation in the exponent to generate partial nonces, Ri, of the honest players that match the value R that he received from the challenger. Now, The simulator knows the SI of the corrupted players. Why does it know the SI of the corrupted players? Because it gave them KI, it gave them XI. And so, given S, it can interpolate the SI of the honest players and compute the simulation. Notice that in this simulation, the simulator was able to run this network on the same public key that was given by the challenger. And for every message, he was able to obtain the same message, the same signature, from the network that he received from the challenger. This tells you what we need to, oh, by the way, so once the simulation ends, if the adversary forges, the simulator forges, like before. And so if we believe the Schnorr is unforgeable in the centralized sense, then this network shouldn't be forgeable either. So this tells us what we need in terms of property for the DKG. We need a DKG that when the end players, they jointly generate a sharing of a secret X, and those are their private shares, and that's the public key. And those are so this is what the protocol should do, right? It should generate a random secret X with shares for the players. It should generate the public key, which is G to the X. And it should generate this public commitments to the shares because I need them for robustness, right? To weed out bad shares, bad partial signatures. So this is what we need for the protocol to work. For security, and we're going to do this once for the secret key and then once for the nuts. For security, we need a simulator that is given as input this public key Y or this nonce R as to produce an indistinguishable view for the adversary on an execution that hits that specific Y. If you don't hit that specific Y, you're not going to be able to do this proof by unforgeability by simulation that I just showed you. There may be other avenues. We'll talk about that later in the talk. But if you want to stick to this proof by simulation, the simulation of the DKG has to match the public key that you receive from your original challenger. Any question on that? Because this is a very crucial point that is going to come up in a minute.
So the chat is quiet so far.
Okay.
Seems to be clear.
Either I lost everybody or I'm doing a very good job. Good. So let's continue. So let's now do DKG. So DKG starts with what we call a verifiable secret sharing. In VSS, players have a guarantee that there is a unique secret share and that their shares interpolated the correct secret. So, once the dealer is not trusted anymore, once we're all going to start dealing secrets and some of these players are corrupted, somebody could pretend to do a Shamir secret sharing, but in reality give random values to all the players that do not lie on a polynomial, and that would sort of mess up everything, right? But Feldman VSS actually prevents that and does it as follows. On input a secret X, the dealer chooses a polynomial, as usual, basically does Shamir, right? It does Shamir, but it also broadcasts publicly the values of public commitments to the coefficients of the polynomial. When the player receives this Shamir share, the player can check that this share lies in the correct point by doing an evaluation in the exponent. Instead of being interpolation in the exponent, now this is evaluation in the exponent, meaning is going to check the linear combination of the coefficient times its value I to the j should be g to the xi. And if it doesn't work, you lodge a complaint, and complaints are, obviously, if there are more than t complaints, the dealer is bad because there is an honest player who's complaining, and obviously the dealer is dishonest. But if there are less than t complaints, you need to decide who is bad, the player who's complaining or the dealer, and you resolve this complaint by broadcasting the correct share, because at this point the adversary knows it anyway. And here we're talking about honest majority. So, or actually it doesn't matter. Okay, so this is Feldman VSS. And Feldman VSS is the base of the first DKG that appear in the literature, which is Pedersen DKG. And what Pedersen DKG does is basically n Feldman VSS in parallel. So every player I performs a sharing of a random value Zi. And because it's a Feldman VSS, the value G to the Zi is public. Remember, I publish all the public commitments to the coefficient, and Zi happens to be the free term of my polynomial. So that's public. Each player receives his own Shamir share from this particular sharing. Let's call it Zij. And this value right here is also public from the Feldman VSS, right? Because it's the evaluation in the exponent of J of the points released by the Feldman VSS. Oops. Now, at the end of this thing, there's going to be a bunch of players who have not been disqualified. And let Q be the set of players who are not disqualified. Then define the secret key X as the sum of this of the random values that were shared by each player. And this automatically we give me G to the X because it's the product of the Zi. And if each player takes his own share of X as the sum of the shares he received, then the public commitment to his share is also public as the product of the local public commitments of each VSS. Okay? Any questions? There is a very... right?
So no, not in the chat.
So there is a very crucial issue with Feldman's VSS, which is that the secret Zi is not information theoretically is not even semantically secure given this protocol, right? It's only protected by this one-way function right here. So it's true that I cannot compute Zi, but I may have enough information to affect the output. The adversary is going to use these values right here to affect the value of the total protocol. And that's going to be an issue when we try to simulate Pedersen DKG. So it's very interesting. Pedersen DKG was the standard DKG that everybody referred to for a long time until we noticed, we meaning me and my co-authors, noticed that there was an issue in trying to simulate it. And that was in the process of building exactly this proof by unforgeability proofs by simulations, right? Where we notice we really have to hit a particular public key and a particular nonce. So let me show you what the issues is, right? So the simulator is receiving a particular public key Y, and now it needs to simulate the execution of the Pedersen DKG so that it hits Y, not it hits any random public key Y. It has to hit this specific Y. So the simulator is going to play the role of the good players, and when each player broadcasts, they do Feldman, right? So this player does this player did this player does this, and the simulator has no idea what the adversary is going to do. Remember, when we simulated Feldman, we gave the adversary, as a dealer, we gave the adversary their shares, so we were able to simulate these guys. But now each player is playing the dealer in Feldman. And so when the simulator puts out its values, they have no idea what the adversary values are going to be. And there is no way that the simulator can hit the right distribution. There's no way that the simulator can hit that target Y, and because the simulator really needs to see the contribution of the adversary before committing to the contribution of the honest players, right? So that basically is why the Pedersen, and this in practice means that the adversary can bias, as I was saying in the previous slide, can bias the distribution of the distributed key generation protocol. Okay, and that's your reference right there. So what we can do is we could, before revealing ZI, we're going to have everybody commit to these values. I'm going to call this a committed Pedersen DKG. We're all going to commit to these values with a non-malleable trapdoor commitment. And then we open the commitment and we do the Feldman VSS. So we add one round to this protocol by committing to the value that we're sharing in advance. Okay. So, and then we continue as before. And now let's see that this simulation actually will work. So the first step, the simulator receives Y. The first step is they all commit to everything. At this point, the simulator can commit to whatever he wants because it's a semantically secure commitment, so there's no problem. Then they all open, and this thing is not going to match Y, okay? But now I know Z4 and Z5. And now I rewind. This malleable commitment, I didn't say that before, I think I said it, but it's a trapdoor malleable commitment. Meaning, now I can change the opening of my CIs. But because it's not malleable, the adversary cannot change it. So I'm going to rewind the adversary, which is a problem because rewinding has issues with composition, but just for simplicity right now. I'm going to rewind the adversary. I'm going to change one of the contribution to Z1 such that Y is really going to be the product of Z1, Z2, Z3, Z4, and Z5. And now I am matching the public key that I am looking for, okay? And the reason this works is that the adversary cannot change this due to the non-malleability. However, what the adversary could do is refuse to decommit. So here, maybe the adversary likes what he sees and he says, I'm going to decommit. But here, the adversary doesn't like what he sees and he says, I'm not decommitting. So the main difference is here is that if we accept abort, because in this case, the adversary is biasing the distribution but in a detectable, in a way in which the behavior, the malicious behavior is detectable. So now if we accept that a protocol that does not successfully complete, then we're going to be able to hit the right distribution. So the security guarantee here is that we're going to give up robustness. So here if the protocol completes, then we hit the right value and we show that it's unforgeable. Or the protocol doesn't complete. So the unforgeability now holds because either the protocol aborts or if it doesn't abort, I can show the reduction. So that is the trade-off with this protocol. If we don't want, and by the way, I'm showing you things in a different chronological order. Our first solution, which is the one that I'm going to show you before, we wanted to keep robustness. We wanted to keep security without abort. And so what we need is a commitment where we can, if the adversary refuses to open, we can still recover the value that was committed. But that's exactly what VSS is, right? VSS is a commitment where you guarantee there is a unique value that is committed, and the value will be recovered once it's time to recover. But the problem is that we want a recoverable commitment that is non-malleable. And so that's why Feldman VSS failed, because it allows the adversary to sort of correlate to the good players. So how do we do that? We're going to use an information theoretically private VSS, because if it's information theoretically secure, it's in particular non-malleable, because now the adversary has no information at all. And then we run a Feldman VSS on top of this information theoretically private VSS just to get the public key out. And we need to make sure that the Feldman VSS is consistent with the information theoretic VSS that we used. Okay, so what is the information theoretically private VSS that we use? Is Pedersen's. The dealer on input the secret key X chooses this random polynomial f of X, blah, 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 that's Shamir. But it does two Shamirs, one with f, where the secret is, and one with a completely random polynomial. And now, instead of broadcasting just g to the fi, it broadcasts g to the f5 and x to this should be rj. I apologize. That should be rj. And sends to the player the two shares, one on f and one on r. You can do evaluation in the exponent the same way in which you did it with Feldman. You just have to do one in G and one in H. But because of this random mask right here, we know that this commitment is information theoretically secure, and so no information about X is revealed at all. And then there's the usual complaint phase and so on. So what is the DKG that we came up with? We call it joint Pedersen, where now we're referring to the joint Pedersen VSS DKG. So the player performs a VSS with a Pedersen VSS on ZI, this information theoretic, and then player I perform a Feldman VSS on ZI. But now it doesn't send any shares because the shares were already sent through Pedersen. It uses the same polynomial that was used in Pedersen. This guarantees to me that this Feldman VSS is of the same value that was shared in the Pedersen VSS. And now the set of players, and then it continues with the set of players not being disqualified. Why is this simulatable? Well, this is simulatable because, remember, the first step, they do the Pedersen VSS. Now, remember that we're trying to get robustness. Because we're trying to get robustness, we need honest majority. Otherwise, there's no point at all to have robustness. But if we're assuming honest majority, the simulator is controlling a lot more servers than the adversary. And in particular, from the shares of the Pedersen VSS of the adversary, he will learn what the secrets of the adversary are. And at this point, he can make one. Now he knows what Z4 and Z5 are. He knows because he knows from the Pedersen VSS. And now he can choose a Z1 so that he can match this value. If the adversary refuses to reveal the Feldman part of the Pedersen VSS, it doesn't matter because you can still recover these values using the reconstruction procedure of the Pedersen VSS. That's what I meant by a recoverable commitment. And now your simulation is perfect and you have also robustness. There's no abort. So, and this is a perfect time to stop. I didn't expect that this was going to be, but anyway. So what we've done so far, we have shown you that with a simulatable DKG, we can construct threshold signature for Discrete law-based schemes such as BLS and Schnorr. If we have honest majority and we want robustness, we use this joint Pedersen DKG that I just showed you. If we are okay with abort, all you have to do is just a committed Pedersen engaging. The proof follows a simulation argument that says that if you can forge in the threshold setting, then you can forge in the centralized setting. What's left, and I think maybe this, we're stopping now, right? It's 9:15 for a break. Hello?
Yes.
Okay, so when we come back, we're going to talk about how to use this thing for the digital signature standard. Okay. Any questions before we start?
Yes, there are actually two questions.
Okay.
So the first question, why isn't it possible to just boot the players not answering and restart the protocol?
It is, but you will still yeah, so you will still end up with a bias key. That's the problem, right? So say that the adversary doesn't like public keys that end with 0. And so you are going to somehow, if the public key ends with 1, the adversary will finish the protocol. And if the public key ends with 0, one of the bad players misbehaved, causes the protocol to abort, we kick him out, and we continue, right? First of all, you need to detect that the guy is misbehaving. But now, the total execution of the protocol is going to give you a bias key. So because, and we'll see that later, that this bias is actually not that problematic in some cases. That will come up in the rest of the talk. But if you want proof by simulation, you have to do this.
Okay, then there is a second question. Can you explain why you need both verifiable secret sharing schemes in the last construction?
Yeah, so let's start again. So remember the committed VSS, the committed Pedersen? So how do I deal with the fact that I want to know what the contributions of the adversary are? Well, I deal with the contribution of the adversary is by committing, they open, then I rewind, and then I change my opening because the simulator knows the trapdoor for the commitment, but they cannot, right? And here you can, so here you could have the abort, right? And this is what the answer to the previous question. The guy might refuse, the adversary might refuse to answer this question. And here you have the abort. There is a bias, but this bias is not a problem if you accept abort. If you don't accept abort and you always want to end, then the bias is going to be a problem. So here, condition to aborting, the distribution is fine. Condition to not aborting, the distribution is fine. But what if I want robustness? What if I want that there is no abort? That once the protocol starts, it has to end. Then you want to make sure that this value Z4 and Z5 are recoverable, even if the adversary does not open them. So we're going to do this VSS. But why do we need two VSS? The first one is to be non-malleable, and we're using a information theoretic one, right? And by the way, this is one way to do it. It's not the only way to do it. I don't know if there is another one, but the reason is that we chose this information theoretical VSS. Once you chose the information theoretical VSS to enforce this non-malleable recoverable commitment, because it's information theoretic, you can't get the public key out. You need to get G to the X. And information theoretical, by definition, gives you no information, including G to the X. So you run another piece of protocol that will get G to the X out from that information theoretic VSS, and we chose to use Feldman. Now, if there are two possible ways of dealing with this. One is to have a non-malleable VSS, which gives you the G to the X in a better, simpler way than running a Feldman VSS on top. That's a possibility. I don't know if anybody has done it. And the other way is to run a Pedersen information theoretically VSS and get G to the X out in a better way than running another VSS. We chose to do it this way, also because the second Feldman is really not, I mean, it is another round, and it's but there is not much computation there because all the commitments, all the exponentiation have already been computed as part of the Pedersen. So at least from the dealer point of view, there is not a lot of work. It doubles the verification time for every player, though, because they have to verify the Pedersen pair and then the Feldman after.
Okay, maybe a short final question. Is it possible to transform proposed protocols in two-party setting?
Not so the ones with a board, yes. Obviously not the one with robustness and honest majority. I am not going to talk much about this in this talk, but there the honest majority. I'll make some references towards the end of the talk today. The ones with a board, they're basically generalization of two-party protocols. So yeah, you have two-party Schnorr, two-party DSA, and so on.
Thank you very much, Rosario. We'll resume after the break.